Hello, good evening. Am I audible?
Yes, ma'am.
Okay. Just share my screen. So, welcome to the uh, tutorial session. This is the 9th week of power electronics applications in power systems. In the last discussion, we we talked about the static bar compensator. And to be more specific, we talked about the role of SVC in damping the power system oscillations. And based on the discussions, we solved some numerical problems. So in this week, we shall discuss about the operation and modeling of TCSC. What is TCSC? Thyristor controlled series capacitor. That is the full form of TCSC. So we will briefly discuss the operating principle of TCSC, different protective components which are present in the TCSC unit, and we will solve numerical problems based on the current and voltage expressions of the TCR unit. Those derivations were done in the lecture video. You can see that. And based on those derivations, we shall solve the problems, numerical problems. So, firstly, we shall talk about the different types of compensators. So first is discrete control device. What does it mean? So there are two discrete control devices, TSSC, which is Thyristor switched series capacitor, and GSSC, which is GTO switched series capacitor. Now, why is it called discrete? Because here there is no control. So thyristors or GTO is a type of thyristor actually. So here there are thyristors, but the thyristors are not controlled. They are either fully on or fully off. There is no partial conduction. That's why they are called discrete. Either the state is 0 or the state is 1. The second type is continuous control device where you have control. So TCSC and GCSC comes under this category. What is TCSC? It is thyristor controlled series capacitor. Then GCSC, GTO controlled series capacitor. Here, the state can be 0, 1 or partial control. So we already discussed in previous sessions that controlling the firing angle of the thyristors can be made partially on. So here, varying the alpha or varying the firing angle, we can control the susceptance basically. Okay. So these are basically series compensating compensators. Okay, these are series compensators. So this is the structure, basic structure of TCSC. So this capacitor is kept is like this. So this is the line, and here there are two branches. One is for the capacitor, another is inductor along with the thyristor switches. Like this. This configuration we have already seen. For TCR, right, thyristor controlled reactor, we have already seen where there is an inductor along with this thyristor configuration. So this is obviously variable reactor. If you control the firing angle, you can obtain a variable reactor over here. But this is the fixed capacitor. There are no switches in series with this capacitor. So this capacitive reactance is fixed, but this reactance value, this inductive reactance value can be varied by varying the firing angle of the thyristors. And a more simplistic equivalent circuit is this, where we just simply represent this whole thing by a variable inductor like this. So there is a capacitor, fixed capacitor. In parallel, there is a variable inductor. Okay. So this is the basic structure of TCSC. Now, along with this structure, there are some additional components. So, and each has their role. So first of all, you can see in parallel with this thyristor configuration, there is this switch. This is UHSC, that is ultra high speed contact basically. So if you just close this, then these thyristors are bypassed, and then the current will flow through this path. Instead of following this path, the current will flow like this. So when you close this, the path will be something like this. Okay, via this. And the thyristors will be bypassed. Why it is required? Because suppose there is an operating condition where the thyristors are fully on. The firing angle, there is no variation of firing angle. The thyristors are fully on. So in that case, if current flows through the devices, then there will obviously be some loss incurred in the devices. Because in practical devices, there will be some voltage drop across the device. There will be certain losses, right? The conduction loss will be there, certainly. So to avoid that, there is this high speed contact. So when they are fully on, simply just bypass them. Then the current will be diverted through this path, and the current will not flow through the thyristors. But this is only when the thyristors are fully on. And there are other components like this MOV. The full form of MOV is metal oxide varistor. This is basically a non-linear resistor, and this is used to protect this capacitor from over voltage. Okay. So this non-linear resistor means the resistance value varies. The resistance value varies. It is not a fixed resistor. It is a non-linear resistor, and this is a protective component. Another protective component is this CB circuit breaker. So when you want to completely disconnect, so you use this circuit breaker, it will break the circuit. And in series with this, there is this LD to prevent very high DI by dt. So these are the additional components. Okay. Now, uh, now I shall proceed to the numericals. The first question is a connected data question. So the first four problems are connected data. So all we will use this data to solve the problems. So 400 kV, 60 Hertz, 850 kilometer long symmetrical transmission line operating with Vs equal to Vr equal to 1 per unit and rated load corresponds to delta equal to 60 degree. The line inductance is 0.72 millihenry per kilometer and the capacitance is 9 nanofarad per kilometer. A TCSC is to be placed at the midpoint of the line. So at the midpoint, the reactance of the fixed capacitor and the TCR are 160 ohm and 10 ohm respectively at power frequency. So this is mentioned that the reactance of the fixed capacitor and the TCR, Thyristor controlled reactor, are 160 ohm and 10 ohm at power frequency. So what is the resonance frequency? Now, if we just refer to this figure, so this is the fixed capacitor and this whole thing, this thyristors and this reactor, this whole thing is the TCR, Thyristor controlled reactor. So omega L is equal to 160 that was given. That is equal to omega L equal to 2 pi FL, where F is the power frequency. Similarly, omega C 1 by omega C is equal to XC, that is the capacitive reactance. Okay. This is inductive reactance, this is capacitive reactance. So these are the magnitudes, and actually we represent them as J by omega C and J omega L. And if we just talk about the magnitude, then this is omega L and this is 1 by omega C. Right. But there will be a resonance frequency where this inductive reactance and the capacitive reactance will be same. And that we can refer as omega R, resonance frequency. During resonance, what will happen is omega RL will be equal to 1 by omega RC. That is the criteria for resonance, right? That inductive reactance will be equal to capacitive reactance. So from this, what do we get? From this expression, we get omega R is equal to 1 by root LC, right? And remember, these LC values are not the L and C values of the transmission lines that are given in the data. So these L and C values are this C and this L. They are not this 0.72 millihenry 9 nanofarad. They are not these values. Okay. They are the parameters of the transmission line. So now how do we find the resonance frequency? For that, first we need the L and C values of the TCSC. L and C values of the TCSC are required. So here omega L equal to 160 is given. Omega L equal to 160. That is given. And the reactance of the fixed capacitor is 160. So basically 1 by omega C equal to 160. 1 by omega C equal to 160 and omega L is equal to 10. Right. And what is omega here? Omega is 2 pi 2 pi 2 pi times 60. because 60 hertz is the power frequency, that is equal to 120 pi radian per second. 120 pi. Right? That is omega. So if we just solve for L and C, we know omega value. We can find out what is L and what is C. L equal to, so 10 divided by 2 pi 60, 2.026. 026 Henry, and C value is 1.657. So we can simply put it as microfarad. So this is 16.57 microfarad. This comes, right? So now we can find out what is resonance frequency omega r. Just a minute. I think I will just check the calculation. So this is coming out to be 1523. 1523. But here the options are given like this: 300 pi, 380 pi, 410 pi, 480 pi. So we will have to see what is the closest one. So the closest one I am getting is option D, 480 pi. If you just multiply 480 with pi, you will get a value near about this. So option D is the correct option. Okay. So here I have again seen the circuit so that we can understand the problem in a better way. So yeah. So the resonance frequency is omega r, and we got it 480 pi. So let's see the next question. Determine the midpoint current at rated load condition. So rated current, they have asked. Now we will take the rated load current as the RMS current. We will not take peak current. We will take the RMS current. Usually whenever we talk about rated current or rated voltage, we represent them in RMS values. So what are the informations we require to find out the rated load condition? Okay, let's see. Firstly, what they have given. So the informations are, so I am representing the line inductance as small l, because capital L I am representing the inductance of the TCSC. So this is small l, that was given 0.72 millihenry per kilometer. This is given 0.72, and small c, that is the transmission line capacitance in per kilometer, that is 9 nanofarad. Okay, 9 nanofarad per kilometer. 9 nanofarad, and this is 0.72 millihenry, right, per kilometer. So firstly, what we'll have to do, this we have solved multiple times previously. Firstly, we need to find out what is ZC, that is the characteristic impedance, which is L by root L by C. And if you just do the calculation, you will find ZC value is 282 point some, just 842. Okay, this is the ZC value. Then we will have to find beta L. What is beta L? Beta L is omega root LC. Root LC, right? So that I have found 46.23. The details of the calculations I am not showing here. You can verify them later. Right. So beta L. Now now we will have to find out what is the power flow, steady state power flow. The steady state power flow for a long transmission line is P square by ZC sine beta L by 2. Why I am writing beta L by 2? Because in the question it was given that the TCSC placed at the midpoint of the transmission line. That's why this beta L by 2 is coming, and here also we will write sine delta by 2. Sine delta by 2. Okay. And what is delta? It was given that for rated load condition, we can take delta is equal to 60 degree. Right? So now let's just find out what is P. So the P value is V, you can take 400 kilovolt, that was given 400 square divided by 2. So this is coming 720. But this is in megawatt, remember, because V square, V was given as 400 kilovolt. So V square will be 10 power 6 will come. So this is in megawatt. Okay, this is in megawatt. Now that we have found what is the power flow, from there we can find out what is the current. What is the current then? The current, RMS current, is equal to, this is a three-phase system obviously. This is a three-phase system, so we will have to use this formula, √3 times VLL. That is V line to line RMS, okay? V line to line RMS. So this is 720 megawatt, and here this is 400 kilovolt. This is 400 kilovolt. So this is coming 1039. So this is slightly different, but we can take the closest option. So the closest option is this one, option D. So I hope you understood how we calculated the current. Okay, so the first step is to find out what is the steady state power. Once we calculate the power, we can, and we already know the voltage. From there, we can find out what is the current. Okay. Okay, let's see the, so do you have any question on this?
And beta L omega under root of LC. इसकी value 46.23 नहीं आई.
Sorry.
The beta is equal to omega under root LC. That comes out to be 46.23, man. So I have a doubt in this.
Yeah, so actually, are you getting some other value of beta L?
I am putting L equal to, which is found out to be 0.72 millihenry. And the value of capacitor which I put is 9 into 10 to the power minus 9. And
Right, right.
omega I am considering 120 pi.
Yeah,
Omega.
right. Yeah, right. So actually, I didn't write one thing. So basically, so this omega root LC, this is the beta value. I should have wrote, so this, then you will have to multiply with the length of the transmission line. Okay. So you will have to multiply it with, which is 850 kilometer. Okay. That I didn't write. That's why I think you got some other value. So if you multiply with L, you will get it in radian. Then if you convert it in degree, you will get this value. Okay.
Thank you.
Okay. Okay. Any other question?
Okay.
Okay. Let's see the next problem. Find the expression of the instantaneous current through the TCR unit if the line current is this at rated load condition. Okay. What is the instantaneous current through the TCR unit? Now here we will have to see the current expressions. Okay. See, this is the TCR unit, right? This is the TCSC unit. This whole thing is the TCSC unit. There we have two branches. One is the capacitor, another is the TCR. Okay. And we will have to find this expression, ITCR. This expression is required. Now, suppose this is the line current, and this line current expression is Im cos omega t as given in the problem. This is the current, and this current is getting divided in this branch and this branch as per KCL, right? There are two paths. Some portion of the current will flow through the capacitor and some portion will flow through this path. And so yeah, this is the KCL equation. And we can also find another equation by KVL, right? What is so this is like very fundamental equation. So if a current ICT is flowing through a capacitor, then the expression of that current is C dV by dt. That we already know. This is a very fundamental equation. Okay, this is a fundamental equation. So, and another KVL will give us the if we just if you just do KVL in this loop, it will give you VCT, the voltage across this capacitor will is equal to L di by dt, right? Why? Because we are neglecting the voltage drop across these devices. We are neglecting them, right? We are neglecting them. So you can imagine this is just a line. This is just like this. Okay. So there is this capacitor, there is this inductor, and we know what is the voltage drop across an inductor, that is L di by dt, and that is equal to the voltage drop across the capacitor, because there are only two components, capacitor and inductor, right? And what is this small u? Basically the small u can be either 1 or 0. If the TCR is on, if the thyristors are on, then U is equal to 1. And if this is off, fully off, then this path is broken. So in that case, this is equal to 0. Okay. Then VCT will be equal to 0. Yeah. Now now you have the expression of VC. If you replace this L di by dt here, you will get this portion, right? You will get this. So dVc by dt is equal to L t square ITCR by dt square. Till this point you understood, right? So we just replaced the expressions. Now, now again come back to this KCL equation where the line current was the sum of the capacitor current and the inductor current. Okay, this is the inductor current, this is the capacitor current, this is the line current. And instead of dVct by dt, you write this portion. You write this. Okay. So this is LC and excuse me. So this is LC d square ITCRT by dt square, and then this is as it is. I am not going to the derivation that you will already get in the lecture notes and the lecture videos. So yeah, so if this is a second order differential equation, and if you solve it, you will get an expression like this. Okay. So this is the transient part, and this is the steady state part. Okay. What is this parameter? Uh, what is this parameter lambda? Lambda is the ratio of the resonance frequency to the power frequency. Okay. This is lambda, and omega r you already know. This is the resonance frequency. A and B, they are the constants. And how to find out the values of these constants? So some initial conditions are required. Okay, some boundary conditions are required to find out what are the values of A and B. So therefore, we will consider the boundary equation conditions. Okay. If you see this diagram over here, this is the line current. Sinusoidal or cosinusoidal, whatever. So this is the line current IT, and this current over here. Uh, so this blue current, this is the current through the TCR unit. Okay, this is the inductive current, and you can obviously see that this current is discontinuous. Why? Because we are varying the firing angle, so the conduction will not be continuous. For some portion only, the the current will be there, and for some portion the current will be zero because of discontinuity in the path. Okay. And this another waveform, this is basically the voltage across the capacitor, VCT. Okay. And some parameters are, some angles are defined. This is the alpha, obviously this is the firing angle, right? And beta, this angle, this is called the angle of advance, right? So this is the angle of advance, and this sigma, this is the conduction angle. This defines the duration when the thyristors conduct. Okay. So after defining all these angles, we can refer to the boundary conditions. Okay. So firstly, ITCR this is suppose omega T1. So at omega T1 is equal to minus beta, this value is 0. And at omega T2 equal to beta also, this current is 0. This is one condition. Another condition is Vc minus beta by omega is equal to minus Vc plus beta by omega, right? So you can see here, the value here and the value here, they are exactly same but opposite in sign. Right. So this gives us the second condition. And utilizing these two conditions, we can find out the values of A and B. And finally, this will come as the final current expression. Okay. This is the final, this is the expression of the TCR current. Instantaneous. This is the instantaneous expression. Right. So now, what we need to know, we firstly need to know what is the value of lambda. So lambda, the resonant frequency we already found out, it was 480 pi. In the first question, we calculated that, and the power frequency is 120 pi. 120 pi. So lambda is equal to 4. Okay. Lambda is equal to 4. And Im value we need to find out. What is Im? Im is the peak value of the current. If you remember, we found out what is the rated current. The correct, so the RMS value was some 1029 ampere. So for the peak value, we need to multiply with root 2. Right. So 1029. One four five five. Okay. Ampere. And other than that, all the values, everything is known. Okay. So till this point, is it okay? Okay, fine. So just we will just see what are the options. So can you just calculate what will be this equation? Yeah. So I will just write it. You can verify by yourself. One five five two. Okay. This this value is coming 1552, and rest of the portion is just time dependent expression. So this is omega t, that is, so this will be 120 pi t, 120 pi t, then minus cos beta, where beta is the angle of advance, and in the denominator cos 4 beta, cos 4 beta, and here, so lambda omega t is nothing but the omega rt, that is the resonant frequency omega r. So this is 480 pi t. Okay. 480 pi t. This is the whole expression. So the correct option is option B. Okay. This is the correct option. So next, find the expression of the instantaneous voltage across the fixed capacitor unit if the line current is again Im cos omega t at rated load condition. Okay. So you can just see the lecture video where the derivation has been done. Okay. So you can just so the voltage expression is basically this, where VC dash is this Im xc lambda square minus 1 and this. Okay. Basically VCT is the voltage across the capacitor. Okay. This is the voltage across the capacitor. So this will be, this will, this you will get by integrating the current. Okay. By integrating the current IC dt, you will get the expression of VC. Okay. So this I am not calculating. You can do it by yourself and find out. I will just say that the correct option is option C. You can verify it. Okay. Just replace the values and see whether you are getting it or not. Fine. Yeah, so I will take a small break. So after that, I will resume the rest of the problems. Okay, so we will come back after 10 minutes. Okay, so let's start the discussion again. Yeah, actually, I mm, I pointed the wrong option. This is not the correct option. Option D is the correct option. Okay, option D is the correct option. So basically, if you just here in the expression of VC dash, there is 10 lambda beta, and if you just express it as sine 4 beta by cos 4 beta, you will get this part. Okay, you will get this part. Yeah, so this is the VC dash part, and this is this integration part. This part basically. Okay, so let's see the next problem. A TCSC unit is placed at the midpoint of a transmission line. The fixed capacitor reactance is 1.25 times higher than the TCR reactance. Determine the relation between the current flowing through the TCR unit and the current flowing through the line. It is given that XC, the reactance of the fixed capacitor, is equal to 1.25 times 1.25 times XTCR. Okay, XTCR. It is given. Okay. Again, we will refer to the equivalent circuit of TCSC. So here, as we already discussed, the current has two paths because there are two parallel branches, and one through the capacitor, another through the variable inductor. Now, what is the equivalent impedance? The equivalent impedance is this, right? Because they are in parallel. So JXC in parallel with JXTCR. This is minus JXC. Why? Because we know the capacitive reactance is J by omega C, right? J by omega C. Sorry. So the capacitive reactance is 1 by J omega C. And if you just take the J in the numerator, then it will become minus J by omega C. Okay. Minus J by omega C. That's why here it is written minus JXC. And this is the expression. Okay, finally, of the equivalent impedance, the net impedance of the TCSC unit. What is ITCR then? ITCR is equal to, so there is this impedance divider is there here. This is the impedance divider. So ITCR will be minus JXC by minus JXC plus JXC XTCR times I. I is the line current. And if you take the ratio, then this is the expression. The J will cancel. So this is the expression. In the question, it was given that XC is equal to 1.25 XTCR. So the capacitive reactance is higher than the TCR reactance. Okay. So just calculate it. You will find the relation between the TCR current and the line current. So this is basically 1 by 1 minus this 1.25. Okay. 1.25. So this will come 5. Okay. What does it tell? What does it tell? So the TCR current, the current in this branch, this current is 5 times the line current. Okay, this current is 5 times the line current. So option A is correct. Okay, option A is the correct option. So this is also a connected question. Which of the following statements is true regarding the TCSC operation? This question is linked to the previous question. Okay. So TCSC behaves as a fixed capacitor connected in series with the line. TCSC behaves as a capacitor connected in shunt with the line. The direction of current flowing through the TCR is same as the current flowing in the line. The current direction of current flowing through the TCR is opposite to the current as the current flowing in the line. So this we can easily determine. See here the ratio is positive. ITCR by I, the ratio is positive. That tells us that, and this ratio has been calculated taking into account all the signs, the sign and the this J. Okay, so that's why it tells that the TCR current and the line current, they have the same sign. That's why the direction of current flowing through the TCR is same as the current flowing in the line. Okay, because their ITCR by I is positive. That's why their direction is same. So similar question is here, but refer for the opposite case. In this case, the fixed capacitor reactance Xc is 0.75 times the TCR reactance. Here, Xc is lower than XTCR. Okay. Here, Xc is 0.75 XTCR. So in that case, what is the 0.75? To refer to the same expression here, if you just put Xc, so this is for case 1, and for case 2, it is 1 by 1 minus 0.75. This is 0.75. Sorry. 0.75. Okay. This is minus 3. See here, there is a negative sign, right? So, so the correct option here is the current flowing in the line. Sorry, here. So this is minus 3. I have given the option wrong. So the current flowing through the TCR unit is minus 3 times the current flowing in the line. Okay. But with a negative sign. So the direction of current flowing through the TCR is opposite to the line current. Okay. Here. Because there is a negative sign. These are two different cases. In one case, it is inductive mode of operation. When this ratio is positive, this is inductive mode of operation, because here most as here XTCR is less than XC, so most of the current will flow through this branch. Okay, most of the current will flow through this branch. But here this is capacitive mode of operation, because here the capacitive reactance is lower than the inductive reactance. That's why most of the current will flow through the capacitor branch. Okay. So let's see the next question. Which of the following compensator operates as a discrete control device? So we already discussed discrete control device means there is no control over the thyristors. The thyristors are either fully on or fully off. So there is either 1 or 0, no in between, no partial conduction. So that will be, this is TCSC, so this is not discrete. Thyristor switched series capacitor, this is TSSC. TSSC. Next is GTO controlled series capacitor, then thyristor controlled reactor. So the correct option is this, because this is a switched capacitor. This is not a controlled capacitor. This is a switched capacitor. Okay. So till this point, is it okay, or you have any doubt? Okay. So in a TCSC unit, the thyristor rating is decided by fixed capacitor reactance, current flowing corresponding to the capacitive mode of operation, current flowing corresponding to the inductive mode of operation, line current flowing corresponding to the capacitive mode of operation. Okay. What does it mean? So if you see here, in this problem we got that the TCR current is 5 times the line current, right? The TCR current is 5 times the line current. If you, so basically, and then in the next question, we found out in the capacitive mode of operation that the current was 3 times the TCR current was 3 times the line current. Okay. So if you take the same net impedance for capacitive mode and inductive mode, you will see that in inductive mode of operation, the current is higher. Okay, this current is higher. And whenever you design a system, you will have to design for the extreme conditions, taking into account the extreme conditions. Okay, so whenever you will design, will depend based on the current in the inductive mode of operation, because in this case the current is maximum, the current is higher than the capacitive mode of operation. So the current carrying capability will be decided based on this inductive mode current. Okay. So that's why the current flowing corresponding to the inductive mode of operation. This we consider while deciding the rating of the TCSC unit. Okay. Okay, the next question. What is the purpose of using ultra high speed contact in TCSC unit? In the beginning of the session, we discussed that if the thyristor unit was like this, so if the thyristor unit is like this, then in parallel there was this like this kind of a contact, which was referred as ultra high speed contact. This is when we close this contact when these thyristors are fully on, and we can bypass them so that there is no conduction loss. We can avoid this conduction loss that will happen if the current flows through the thyristors. Okay. So the correct option is to eliminate the forward conduction loss in the thyristors when they are fully on. Okay. Next question. Which of the following operating mode is used to protect the capacitor in the TCSC unit from transient overcurrent in the line? So there are various operating modes for a TCSC unit. Okay. So suppose this is the TCSC unit. Okay. This is the TCSC unit, and here we have the thyristors. We have the thyristors here. Okay. Now one mode of conduction is when these thyristors are fully on. We just discussed that, right? When they are fully on, in that case, there is this combination. Okay. One capacitor and one inductor like this. Now this is a fixed inductor. Okay. This is a fixed reactor or fixed inductor because now the thyristors are fully on. This is called the bypass mode. Okay. This is called the bypass mode. This is the first one. The second mode is when the thyristors are fully off. So the thyristors are off. So this is open. This path is open. There is nothing here like this. So in that case, there is only this capacitor. But this mode is usually not operated in this mode. This is called the waiting mode. This mode is like the mode. This mode is when does it come? This mode comes just before the Varnier mode that I will tell. So what is Varnier mode? The third mode. Varnier control mode is this mode when the thyristors are partially on. Actually, the conduction is partial conduction when we are varying the firing angle. Okay, that is called the Varnier control mode, and it can be in inductive mode or capacitive mode. So just before we start this Varnier mode, this mode is there. This is called the waiting mode. Okay, but actually, like normally this mode is avoided. Okay. And for protecting the capacitor from transient overcurrent, we use this first mode, which is the bypass mode. Okay. This is the bypass mode. This we use to protect the capacitor from overcurrent. So this is the bypass thyristor mode. Okay. And this is the blocked mode. This when they are open, this is called the blocked mode. Fine. Okay. So is there any question? So yeah, this was the last question. Yes. Do you have any question? Tell.
So ma'am,
Yeah, can you please repeat? I couldn't hear you.
so ma'am, all the questions are perfectly understood. Thank you, madam.
Your voice is breaking.
Ma'am, all the questions are perfectly understood. There is no doubt.
Oh, acha, okay, okay. Sorry, I actually your voice was breaking. I couldn't hear. Okay then. Okay, fine.
Thank you.
Yeah, thank you. Thank you for attending. We will meet in the next class.